So yesterday had featured discussion uh, heavily around, appropriately enough, um, matters of interfacing modeling with the contemporary context in which data science, uh, the use of big data, and the the use of artificial intelligence and machine learning as a component of the data science uh, are central features of the extant situation. And we we spoke about this from a number of angles, and I offered some somewhat discombobulated remarks on uh, some tools of systems data science. This bringing together of data science and system science, where the whole is greater than the sum of the parts, where elements of system science can be firmly informed by and updated, uh, elements of theory challenged by uh, the existence of a larger high velocity data availability, where we can use data from the world to infer under to give us some understanding of the requisite level of modeling detail that is needed to characterize kind of observed dynamics of a system, in terms of the level of disaggregation of a model. These are techniques involved in understanding from state space reconstruction, for example. We can recognize when a system's behavior has changed in notable ways in terms of its underlying dynamics. And we can do so drawing on data, either one time series or many, to give us a deeper understanding of the underlying process that can inform our design of a model. And I didn't speak about that in detail, but there are many specifics that are very well established and quite rich in that area, including using empirical time series to better understand causal relationships and whether A is driving B, B is driving A is driving B, and vice versa, so reciprocal, or whether some other factor C is driving both A and B. We also talked about other uses of data there to sort of reground a model periodically, to update our understanding of model state, to estimate model parameters, either in a distributional sense or in a sense of a particular point estimates. But by the later slides, which I ended up eliding in the interest of time, they get into more modeling frontiers that are being actively explored, but are more challenging. And these related to some of the really interesting discussion that Sarah Metcalf here helped stir up on and helped inform and lead on the use of large language models or generative models, transformer-based models as underlie large language models, but can be used with other structures as well, to help in stages of the modeling process. And, reflecting on all this and not wanting to be at risk of not seeing forest for the trees, I decided that, in the last half hour here, that I would put together some characterization of kind of my view of different interfaces of AI and machine learning, with machine learning being a sub area in my view of AI, an area of AI that is grown to be an important building or important contributor to many areas of AI, but is not all of AI. But machine learning, the ways in which machine learning can be used together with dynamic models. And I listed all of these as some explored uses because they're areas being actively probed and explored. I decided to arrange them also very roughly, and this is more notional than any firm, according to any firm metric, but in an order of sort of increasing challenge and difficulty and ambition, and not just ambition often, but indeed challenge or the difficulty in achieving it effectively, in my mind. This is as so much of this is kind of my take, which is very much subject to limitations. Several of these were the province of considerable comment in yesterday's presentation I made on truncated presentation on tools of data science. This idea of, for example, arriving at estimates of model parameters or distributions thereof using machine learning techniques goes back many, many years. And indeed, the primary tool for calibration within any logic, finding model parameter estimates such that the emergent behavior from a model best matches observed data. That process is guided by elements of cutting edge AI as it existed, 15 years ago. And I particularly highlight genetic algorithms in there. Beyond that, though, we also talked about using tools like Kalman filtering, now 60 years old, or much more contemporary tools like particle filtering and particle MCMC, very contemporary tool and very powerful one that's a bread and butter technique in our day-to-day work, to provide estimates in the form of distributions over samples from distribution over model state and model parameters jointly for PMCMC. Particle filtering and Kalman filtering estimate the model state over time in a situation where how that model state evolves is uncertain. It's a stochastic model. We've seen stochastics in the context of our agent-based modeling, and indeed they're a feature of many modeling traditions, including discrete event simulation. And here, if you had a model of a stock and flow model, you would render it in a form that admits some stochastics. It somewhat for matters to capture, for reasons to capture some stochastic variability in its results and to capture some degree of epistemic humility in recognition that we don't have a very detailed, grounded understanding of all the processes, that the model has some limitations. It has some oversimplifications. Elements of it will become outdated, even if they're fully current in their estimates. And so we introduce some stochastics to reflect a degree of uncertainty, of process uncertainty. It's the classic term that would have been used, 60 years ago in the context of Kalman filtering, and which holds true today. So the evolution of the system has some stochastics, and in the broader approach of statistical filtering, in accordance with that, particle filtering, Kalman filtering, and the core particle filtering component of PMCMC basically infer at a given time what the actual state has been, reflecting on the fact that while there's a lot of uncertainty about how our system might evolve, happens in the world resolves our uncertainty about what would happen to a very particular realization, a very particular set of outcomes. The outbreak did happen in La Loche, but it didn't happen in, in a member of a set of Hutterite colonies. It did happen in the core area of Saskatoon, but not in Regina or what have you. So here we have some uncertainty about the world. Observations from the world resolve our uncertainty about how things will resolve with respect to observables, and we reground the whole model state estimate to be consistent with that in a way that admits that there might be many underlying states that are consistent with that, and there's a distribution over those underlying states. This is a very, very powerful technique, and it's even more powerful when it's combined with model parameter estimates for desired parameters, as PMCMC does. And these tools are key tools in the arsenal used for robotics and for modern sophisticated observation systems that interact with the world. And they are very, very well suited in the health area to keep our models current. They can be combined, something like particle filtering and in principle particle MCMC can be combined with agent-based modeling. There are some interesting scientific questions how to do that most effectively. It has been done. My student Kirk Kruger has looked at it, and there's some publications in the literature that even then in 2017, 2018 were reporting favorable results. It's my belief that it can be likely a quite effective method to keep agent-based models grounded and observed in the observed reality of what's played out, much as you would, per my analogy yesterday, reground your understanding for a weather model to predict forward. Before predicting forward, you would reground it in understanding what's happened every hour in terms of the weather in your locality over the past few weeks. And that would give it requisite understanding about how much precipitation has already fallen, and how variable the temperature regimes has been, and the level of wind-induced evaporation, such that its estimate forward is informed by a really good understanding of what the current state is, much more grounded than you'd get just by observing things right now, or what you would get with a model run based on its estimates from 3 weeks ago. Now, another potent use of machine learning or AI in the context of agent-based models was mentioned by Nesrine Jamali here, and that concerned supporting agent reasoning. I should be corrected in that. It's agent behavior, and that could involve risk perception. It could involve actions undertaken in response to a perceived opponent or adversary. Think about the cat and mouse game that was played over decades between tobacco regulators or public health agencies on the one hand and tobacco companies on the other, or between the folks trying to sell vaping to adolescents and those trying to regulate it. You could also raise the same concerning actions in the sphere of online disinformation to try to evade estimate, attempts to warn against it. So here there are sometimes these kind of evasion games and cases where an agent's repertoire can be highly variable. and can respond to the circumstance. And AI and machine learning can support robust tools for that. You can also have agents employing decision-making strategies that use ABMs for some purpose. So there's a published paper we have with one of my students, Narjis Shojati, now graduated, where a agent involved in province-wide regulation of the prescription of opioid painkillers is using a simple machine learning model to identify possible cases of misuse and use them to recommend to physicians possible need to discuss with the patient and better understand if the patient is trying to engage in doctor shopping or abuse. So here, the machine learning or AI is used by agents to sort of provide perhaps a richer and potentially more behaviorally plausible strategy for how people might behave in lieu of, instead of assuming very rigid or very pre-specified or very stylized behavior based on projection forward of certain patterns or what have you. And certainly this is being employed and offers some opportunities. Some of the wonderful discussion with Sarah there, in that discussion, I commented on some of my experience using large language models, transformer-based techniques for working with natural language to help brainstorm possible scopes of models in complex areas, in areas that might otherwise involve many agents. Otherwise involved. They're descriptively complex areas where, given your modeling goals, it might not be obvious at what level you'd be best starting off to approach it. How you might most fruitfully scope the model to get that appropriate balance between the model scope and model complexity and challenge of building it, challenge of transparency on the one hand, with the need to capture some salient behavior about the current situation, and to do so with enough understanding of the causal linkages that you can ask any requisite counterfactuals, any requisite what-if questions that in which you're interested. And this, I noted yesterday in a separate slide that often I find people get confused, particularly with agent-based modeling, about the difference between model conceptualization, formulation, and implementation. They kind of glom it all into computer programming or something. And I indicated my conviction. And I, as someone who is highly involved in software outside the modeling area, I think it's a very informed conviction that this simplification shortchanges really important distinctions from the standpoint of skill sets, from the standpoint of barriers, from the standpoint of staging of a model and conceptualizing the different sets of stakeholders that are needed at different stages, etc. But I noted also that, in my view, model conceptualization and formulation, recognizing we're talking about an iterative modeling process, is the foremost barrier to most modeling. The implementation does have barriers, I noted, for those without a computational background, and I'm not trying to minimize that. I sympathize, but in the context of today's environment, particularly, a lot of the basic lower level, when I say lower level, I mean not designing the architecture of a system or here a model, but the sort of filling in the bits of coding needed in places. That's becoming much easier for a variety of tools, including generative tools. The use of tools like Copilot, but also the code related tools for many general purpose programming languages that are increasingly available do make creation of small bits of code that need to be created much, much, much easier. Also, I am finding many health scientists now come with at least passing familiarity with writing code in something like R in a way that is rather different. I mean, it's markedly different in my experience than 10 years ago or 20 years ago, where the idea of programming and coding seemed like a big challenge for many health scientists that I encountered. Really, they felt it was outside their wheelhouse, and maybe you'd use SAS and call various procs, but there wasn't much awareness of performing actions computationally. And I would credit R for building an engagement with R and the need to engage with data in that context as growing more skills on the implementation front. But the conceptualization and the formulation side are where I think a lot of the key barriers and key opportunities are for modeling. And there's a sense of being able to nail the problem with the right scope that has that good balance and that has the requisite hooks to capture essential features and to allow you to perform the analyses that you're interested in, and where appropriate to interface with appropriate empirical sources of data that might inform model parameters or allow you to calibrate the model. So there's a real challenge getting that well articulated. And I do find, based on my experience, large language models sometimes helpful muse or sort of companion that I could say, okay, so I would, give me 3 different scopes you might use for this model and characterize. And I use that for my brainstorming. I use it for my consideration. This is quite new, I will note, and it's not driven by a sense of deep need, but I do think that sometimes I can get caught up in a bit of tunnel vision, and I need to sort of I need a stage of divergence before I converge. And sometimes I may be at risk of converging on an idea that hasn't considered a sufficiently broad set of alternatives. Now, mind you, what I'm asking them to do is at the conceptual level here, and this is not using large language models to produce a fully born model or anything remotely like that. It's more a matter of scope and concept and sort of in broad terms what it would include, what it would treat as endogenous, exogenous, ignored, or what have you. And that's useful. I find that useful for my thinking to be able to bounce ideas off of it. And I would argue that this is a appropriate use in software as well. Just giving you design ideas to make sure you're not overly bent on one path where you should be considering something a bit broader. Maybe it can jar you out of a blind spot, and you recognize, oh yeah, that's right. I need to make sure I take this into account. Formulation of models, I put it down there as harder, yeah, although I think conceptualization in some sense is the most challenging part of a really good modeling project. For me, formulation, and for my students from observation, and for modelers from what I've been able to tell in general. Model formulation, the sort of unpacking that into mathematical relationships, the sort of conceptual and mathematical building blocks, unpacking it into mathematical processes that we characterize, discrete, continuous, in ways that are at both elegant and admit the requisite extensions, admit the hooks to put in interventions, provide the requisite level of summary to compare with empirical data, potentially be to support calibration or to support model validation and confidence building, to provide the outputs for stakeholders. This issue of sort of the formulation, how we unpack it into mathematical structures. I find that there's quite a lot of art there. And when I say art, I mean in the sense of practice-based skill that's built up over decades, and tacit knowledge as well as explicit knowledge in certain recurrent forms. Like, these are good ways to approach this issue. This is a good way to characterize a process like this. And I find for teaching my students that tutorials along these lines are often a key part of building on their journey towards being full modelers. I do not have, and I want to make this clear, I do not have grounded experience at any meaningful level of using AI tools for formulation. However, I will note that when I draw on approaches for characterizing certain processes in ways that are elegant and simplify the situation, etc., I draw on a lot of knowledge from past models, from the literature. When I say past models, I don't necessarily mean by myself, models I've seen elsewhere, ways things are done in the physiological modeling literature that I've seen in some other agent-based model, or a good approximation that I've seen in the applied mathematics literature, etc. And the very fact that those are in the published literature, that they are incorporated as idioms and patterns in a lot of extant model descriptions, coupled with the fact that we are emerging from an era where the ability for AI machine learning used to be completely risible with respect to capturing mathematical structure. It was a cruel joke to try to elicit some understanding of mathematical structure from an AI model. And it would, with great hubris and certitude, assert that you should do it this way, and it exhibited no sense of self-awareness of how impoverished its answer was. It was pathetic, in a word, and it was arrogantly pathetic for many, many years. What I'm seeing now, and this is like the last 2 or so years, is turning increasingly turning a page, I think, on this because of a lot of investments in these models to improve their ability to reason logically, to improve their ability to reason in ways that capture mathematical invariance in relationships, that retain basic understanding of mathematical structure, ways that were completely pathetic before. And I haven't done my homework on this, but I do know that the results here are really that are being published in this sphere in papers or being shared out of professional meetings are quite striking departure from what was there before. Some of you may have heard the competitions in which AI large language model tools equipped for mathematical reasoning or for computational with coding as well compete against other human users. And when they've been able to just regurgitate answers that are out there to known problems, that was never the issue. That was just regurgitation. It was just recapitulation of some quasi-memorized thing, so to speak, reduced to some features of it. That regurgitation is something that's long been good at. And some of you may encounter Noam Chomsky, who revolutionized linguistics and undercut the scientific scourge of behavioralism that existed in thrall of science's thrall for probably a decade at that time, and was a groundbreaking, towering scientist in the linguistics field. I think probably the single biggest figure, probably by a notable shot in the 20th century in linguistics, and a mathematical someone with great mathematical skills. You may have come across his commentary on AI models as regurgitating, and there's some reason for that for many years. But so for many years they were able to regurgitate published problems that are widely accessible or bits of code, and they would spit it out in ways that were really problematic sometimes. Like they would steal code from code bases which have well-defined licenses that you couldn't do that without using the results for free distribution, and they would just blithely ignore it. There were a lot of problems with it, but it would regurgitate very readily. But in the last 2 or so years, what I've heard is something altogether different. So for the Math Olympiad, for example, AI competes at a gold level, a gold star level, gold medal level. And in my time, I've had the pleasure of knowing several gold medalists in the Math Olympiad. And I understand the level of mathematical depth of knowledge and repertoire that those individuals have, and AI is competing at a level comparable to very, very high level response to mathematics competitions. This past spring, there was a very active testing of one of the extant language models that's just come out, where a set of mathematics professors gave it a set of foremost problems, including many novel problems, and asked it to solve them. And they declared it at the level of an outstanding, like, second-year doctoral student in mathematics. A very, very talented second-level doctoral student in level of reasoning. I would love to have a very talented second year doctoral student who with very strong levels of mathematical skill in doctoral student in mathematics. Um, uh, I think UJ would qualify for much of that, but the point is, it showed a level of flexibility and repertoire and depth of understanding how to approach word problems that had never been seen before. That was really thought-provoking. My colleague, Chris Duchin, um, who co-teaches in my department and has for, gosh, over a decade led the um, programming programming contest every year for programming teams and led several teams to medals in various areas of Canada, um, has reported that uh, the best teams are now regularly outcompeted, and in the past year or so, outcompeted very strongly in novel programming problems or not widely circulated programming problems by large language models equipped to reason about that and mathematically. So this is a very fast changing area. And I do believe that mathematical formulation, this brainstorm formulation, which has been a big area of challenge for building models, like how do you unpack it into that without being apprenticed to someone for decades? Like that is starting to show some openings to improvements. Now, as stated yesterday, what the key need here is to be savvy enough that you can critique it, know when it's off base, know when it's all wet, when it's suggesting something that just won't cut it. And that does take understanding on your part. It's not a matter of outsourcing your understanding to it, but it's a matter of being really savvy about, okay, is this something which is a genuinely good idea, or is it just something that is confidently rubbish? And I have seen both. Um, so just be aware. I think this is an area of rapid development, but one thing that's not rapidly developing is the key need, the absolutely essential prerequisite that someone using these tools be in a position to assess the results, to critically evaluate it, to find it wanting at times, and figure out where it's reliable and where it's not. And that's going to require human training. It's going to require apprenticeship. It's going to require guidance. It's going to require partnership with expert modelers or what have you. So those challenges are not going away, but it may be that there's a certain broadening of the idea of really good idea generation that can then be tested through appropriate collaborations and where needed through peer review. Um, so so those two, I think, in my view, those two have come a long way in the past few years. I started to see it on, a lot of hope on the conceptualization side is, back in 2023. And my sense is in the past year, the model formulation side is increasingly coming within kind of striking distance of where it's a fruitful exercise to try to brainstorm about formulation and to try to use it to arrive at improvements to your ideas and cross fertilize your ideas and broaden your ideas, etc. Be part of a brainstorming discussion without outsourcing it. Next, I'll mention there's some really good work going on, and I want to highlight particularly the work of Brunton and Cutts at University of Washington for their work on um, data-driven machine learning. And I should have their book up here somewhere, but it may actually be out on a desk here. But Steve Brunton and Nathan Kutz are, in my view, some of the most uh, visionary and active researchers in this area who um, are providing ways of um, engaging with data volumes, including the sort of data we might see in health, particularly in the context of smartphone-based data collection or wearable-based data collection, as we're involved extensively and including our own platform used for it. And taking that data and using it with machine learning in a way that learns more deeply from the data rather than just estimating parameters or estimating the state of the system over time, or just fitting some deep learning model to best match the data given the data generating process and finding that it breaks when some counterfactuals introduced, when the arrival of a new therapeutic, or when vaccination is introduced. Rather than doing that, what they're doing is seeking to do two things that I think is quite interesting. One is to infer. So if we have a model with a certain mechanistic characterization, to try to figure out the residuals, where that model goes off from the empirical data, and try to train models that will help correct for that, so that the theory-based model dynamics can be supplemented by parsimonious, you know, um, extra hints or assistance, an extra hand up to allow it to capture some dynamics that you're not capturing well in the current model. Now, there are shortcomings of this. This is not without its issues. As people say, both for this and for things like particle filtering or Kalman filtering, you don't want to let this hide a bad model. Like you don't want it to just bury the shortcomings of your model. Remember, modeling is learning, and you don't want to shortchange the opportunity for learning for just saying, well, go correct whatever problems you see. Like maybe there's some important insights to learn from when the model is just not jibing with certain aspects of the data. But to the degree that you're in a production capacity, to use language of data science here, to the degree like you have a model that is being used day in, day out for certain purposes, like ours was, throughout for all Canadian areas during the pandemic, the provinces and then the First Nations reserves. They're like you don't you do want to take into account the unique features of the situation. And this idea of kind of residual modeling, of like nudging the model to take into account these extra things that it's not taking into account now, and reflecting on them on an ongoing basis and asking, what does it teach us? If you incorporate that in the learning cycle, I think it can be very helpful. And they're doing some interesting work on those lines. I think more deeply uh, is there more deeply interesting in my mind yet is their work with CINDY, the sparse identification of nonlinear dynamical systems. And again, I'm looking for their book, which I'm frustrated I'm not finding here. Sparse identification of nonlinear dynamical systems, SINDY, and also some cognate tools like neural differential equations, in which they also teach, which basically seek to arrive at mechanistic descriptions of a system by inferring aspects of its inferring descriptions, characterizations in simple mathematical terms. In the case of the first of those, in symbolic terms, formulas, that best match the observed data. So here it's kind of sorting through all this observed data and trying to arrive at a description that's very parsimonious, that is able to express the requisite breadth of behavior and characterization of behavior across many areas in a very parsimonious way, in a way that's elegant and short and descriptive. Now, they've had a great deal of success of this with physical systems, both more sort of simpler lumped systems, like inverted pendulum and kind of multi-pendula connected to each other. Also with and that would use what are called ordinary differential equations, so essentially things that could be translated to stock and flow models, but also with systems which admit other dimensions, like we described with partial differential equations, and evolve in space, etc., like with fluid flow. But put aside the area, they have done some work with collaborators and applying this to public health, although I'm not seeing much emerging yet from that. But the basic idea here is to try to learn, as it were, mechanistic rules from observed data, and I think that is an interesting challenge when we have diverse data sets of enough velocity, length, volume, variety, that one could piece together a simple, consistent description of the system. I put it down there in the second to last bullet point because I think it's very, very challenging. And one of the things that it in no way addresses is the contingent nature of those on the data generating process. So, like, this is still subject to needing to be changed wholesale, or changed in very significant ways if the underlying dynamics of the system that are being described parsimoniously were to be altered. That will change the data, but it will also change, by and large, typically the description that best matches that data. So, and it's also not necessarily admitting a causal description of the system, one that would be fit for asking counterfactuals. It's possible that it is, because this is not combined with work like CCM to identify causal connections and estimate their strength, their relative strength. It doesn't necessarily pick up relationships that are assured to be causal. There's really exciting work going on causal AI that is still in its early stages, in my view, but maybe which could eventually inform this. But right now, this is an intriguing idea, and it can again help improve model building, help give us a leg up on model building, help give us some ideas how to describe a system more parsimoniously, which is something which could be really valuable to help refine our thinking. The final challenge, which is one where we alluded to some yesterday, is, in my mind, it's it's some distance away at scale in realistic health contexts, for several reasons, but it's to generate full-blown articulated dynamic models that evolve according to successive identifications of needs and goals that have the requisite matching to empirical data sources, that have the requisite ability to examine whatever interventions you're interested in, that are informed by the appropriate data sources that are properly matched against data sources that get compared with empirical data, and that depict things in a way that's mechanistically plausible and causally plausible. I think that's a a big challenge. I think there are some very simple models that might be able to be described in this way, uh, with appropriate prompt engineering. I personally tend to be um, fairly skeptical given the human theater involved in modeling. The fact that it's the modeling more than the model that offers the value, that it's a socio-technical process, that it involves building confidence, it involves dialogue, it involves a sense of people needing a sense of having their voices heard, a sense of being empowered, a sense of having ownership, and a sense of um, uh, having had a say in informing the model. I am skeptical at a socio-technical model that models built, even if they could emerge full-blown, like Athena from Zeus's head, as I've said, I'm skeptical that they would secure acceptance. But more than that, I am skeptical that they would offer uh, more than a small fraction of the value of a model built up um, organically through a team-based process with interdisciplinary stakeholders and people from many backgrounds, and often people affected with lived experience of the conditions, because the key component is informing the mental models, and that mental modeling, that informing the mental models occurs during the modeling process. I will say, I co-teach AI for public health. Um, my teaching on it varies from core AI topics to topics in systems data science, to topics on the data science side, like federated learning, um, and differential privacy, and secure aggregation in those contexts, and homomorphic encryption. Um, so not all of it is strictly machine learning by any means. A lot of it is broader, supporting data science and techniques for privacy preservation and equity enhancement. One thing that I am seeing that is very disturbing to me, very disconcerting, is the prospects that um, that many of these students um, are increasingly turning to AI techniques as kind of um, things that they undertake mechanically in R, or variously in Python. They treat them as, well, I'll just make this function call and I'll get back a trained model, or I'll just okay, and here I'll train a neural network, here I'll train a random forest model, or here a decision tree, here a random forest, here a support vector machine, and I'll see which of them does best, and I'll declare victory. I'm oversimplifying a bit, but I'm seeing a lot of kind of viewing machine learning and viewing application of AI as kind of a step to be undertaken to match data. And that profoundly unsettles me, because I think what we most need as a society one of our greatest needs is to think deeply, hard, and empathetically with real understanding the human conditions involved, what the data means, how does it relate to people's actual experiences, the textures of their lives, what does the data include, what does it not include, what does it pick up, what does it ignore, who's included, who's not included. And while we talk about those areas, to be clear, in AI for Public Health at great length, while we talk about the importance, well, at some length, while we talk about the importance of equity issues with data and making sure that data is not disproportionately favoring certain groups, or that machine learning results don't disenfranchise, give results because of class imbalance or other reasons that favor one group or another. While we say that, the actual practice of it seems to me, from observation, to be increasingly mechanical. It's viewed as like, oh, I'll undertake this step, that step, that step. It's undertaken in a procedural way rather than a way of understanding. And if there's one thing you take from this boot camp, I hope it will be thinking about modeling in the broader human context, in the human theater, and think about how it teaches us to think through more deeply areas of the world that we may not recognize, and helps spot blind spots within our thinking, helps us remove blinders, helps perhaps draw us by conveying stories like those stories in Wade's water model yesterday that connect with actual people's experiences. These things are really important. And, to the degree that AI tools are coming to help empower those, like those here, like many of those here, I think, particularly the first 5 or so, and rightfully done, the next couple, I think it's, to the degree it's supporting it can be good. But what I fear is falling into a pattern where, for shortage of time or lack of understanding, lack of genuine knowledge, lack of authentic understanding of the craft of modeling, or the, how AI algorithms work, or just out of laziness, it's just treated as a mechanical process. If AI can generate, okay, we'll generate that, time to move on. We've got to meet the deadline, and you don't actually think it through, and you don't connect it to people's lives, and you don't connect it to their stories, and you don't think whose stories are ignored. I'm deeply concerned about this. And, there's a saying I sometimes like to talk about, and we fall short of it, but I think it's a good target to aim after. No AI about us without us, no modeling about us without us, like being able to listen to people who are affected. Peter Hoffman talks about the dignity of risk, and being able to make sure that the people who are affected, put at risk by decisions, have a say in that, and have a genuine voice to inform it, have a voice about what the data about them means, how to interpret it. And I'm a big believer that this is where we need to go. And we need to watch out for anything that, by its design or by its de facto placement in the rough and tumble of people's daily working requirements, daily working obligations, ends up being used mechanically, ends up being used as just a procedural step. We got to make the donuts. It's time to generate this, time to apply this model, without really thinking, what do they mean? What are their shortcomings? Where is this model going to fall short? Is this really a good use of this model? Is the data suitable for use in this way? These are important questions, and they're not mysteries of the Sphinx. Like there's really good understanding behind them that someone who's actually trained deeply in these areas brings to bear. And if broadening the set of people trained in these leads predominantly to impoverish that side of it, that side that is so important to connect to real human, the fabric of real human stories and existence, I think we will have done a disservice. And this is what I fear, I see elements of an AI for public health, not because of any shortcoming on the part of my co-leads, but because of the reality of the current context. So I did want to reflect on that a little bit in my own convictions, my own experience, my own observations about different levels of challenge in the state of play in this very important area. So I think I'm going to stop there. I think we'll afford all of us a